Okay, welcome back, everyone. Last week we left off our discussion on basic steel alloys, and we'd gotten into the basic categories of plain carbon steel alloys, low carbon, medium carbon, high carbon. Then we talked a little bit about stainless steels, etc., etc. And so I wanted to start off today and finish that up a little bit, and more comments on the alloying elements that are inside most steels, and what they offer, what they give up to the steels, and then we'll get into heat treating. And then from the heat treating, we'll move on to the time temperature transformation, aka the isothermal transformation diagrams and curves, and then have a final discussion on hardenability. Now, we're not going to get all that in 15 to 18 minutes, but so this will probably take 2 or 3 videos to get all this in. But be that as it may, we're going to get going and get started now. I will tell you that on my video channel, I would hope that you would have or will watch this wonderful. I have a video called Heat Treating on there, and phase diagrams, and it's an extremely well done short video clip of basic processes involving heat treating and a little bit about the iron carbon diagram. So I truly recommend that you watch that. I think you'll gain quite a bit from it. Okay. Now, so again, last week, left off with basic steel alloys, and essentially just talking about their carbon content. And so I've got steel alloying elements here, and essentially carbon is always going to be inside of steel. Of course, that's what makes steel, the combination of iron and the interstitial addition of carbon into the iron atom, which makes steel. And we know that steels are all basically less than 2%, and most commercially available steels really stop at around 1.5% carbon. After that, it's pretty much designated as different types of cast irons. Anyway, so as an alloying element to steel, as there's some changes that go on that happen as incremental amounts of carbon are added to the iron. These following categories exist, and so as the carbon content increases, the steel becomes, of course, less ductile. And of course, we know what ductile means. It means the ability for that material to be able to stretch in a tensile mode without it breaking. So it becomes less ductile. It becomes easier to harden, which is what we're going to be talking about in quite a lot of detail here shortly. So the more carbon you add, the easier it is to harden to various degrees. But also it becomes less machinable, which means it's more difficult to machine. It's more difficult to remove the metal from a component. If you're machining something, making something, either turning it or milling it, what have you, you're going to be removing a certain amount of steel to conform to some sort of geometric shape that you're trying to produce. So it becomes less machinable as the carbon content increases. It also, there's a benchmark welding percent of carbon, and it's called the weldability percentage, because anything below 0.3% carbon is considered to be weldable. You can weld two base metals together, fusion welding wise, and there shouldn't be really any performance issues as long as the weldment itself was performed by someone of relatively skilled welder. But essentially anything below 0.3% is usually fine and can be specified to be welded. You won't have any issues performance-wise. However, anything above 0.3% carbon content in steels becomes less and less weldable. In other words, a little more difficult to weld, and a lot of times even not even recommended to be welded, especially if it's in some sort of structural application that's going to be have subjected to a lot of different types of stresses and forces and loads, dynamically, statically, whatever. It becomes very sort of difficult to get those steels properly welded to perform the way they should. And so there's lots of, not saying you cannot weld steels in above 0.3%, but it requires a lot of different types of operations, both pre and post weld applications. So just keep that in mind at that percent. Okay, and then also as the carbon content increases, it increases, the steel has a higher tensile strength, higher sigma max, as the carbon content incrementally increases. And remember, we're just talking about very small amounts here. 0.1, 0.2, 0.3, all the way up to the eutectoid composition of 0.8. So we're not talking about a percentage here, as opposed to when we were talking about stainless steels having high chromium contents in excess of 11%. So it makes a lot of difference in that. So, okay, so let's look at what I consider to be the top 5 alloying elements that are added to a lot of steels for various sundry reasons, but of course most of them for specific increases in their overall properties, and we'll talk about what those are here in a minute. But the top 5 I listed here in alphabetical order. Chromium, of course, is one, and these are just alphabetical. But chromium is in there, and as you already know, chromium's added to most steels to help with its corrosion resistance. But more importantly, as I mentioned last week, also it really raises the temperature applications of that particular steel as the chromium content increases. The steel improves its overall performance at elevated temperatures. That's one of the reasons they add a lot of chromium to steels. And then we have some other elements. Manganese is usually always added. Molybdenum is always added, and primarily these two are adding in helping to increase the hardenability of that. Nickel is added quite a bit, along with, in specific applications, vanadium is also added to a lot of different steels. Now, I'm not going to go through the details of what each one of these elements bring to the mix, so to speak, but generally speaking, the effects of most of these alloying elements that we talked about have the following effects. First of all, they call deeper hardening of quenched and tempered steels. Now, this may not mean a lot to you right now, but later on, once we get into that heat treating, you'll understand a little bit better. But essentially, you're going to be able to harden something to a lot greater depth than you could without some of these alloying elements. So, and we're going to talk about what the quenched and tempered steels are, but it makes it for a deeper penetration of the hardness into that component by having some of these alloying elements in there. It also, of course, and one of the main reasons is that, generally speaking, is it improves the overall mechanical properties of the steels, but specifically at high and low temperatures, both. So instead of just having the same properties, now you can have those properties at extremely low temperatures, because we know that steel has some issues with respect to low temperatures. When we talked about the ductile brittle transition temperatures for different alloying steels, that can cause severe brittleness, the loss of toughness. But then also at high temperatures, again, it helps to improve their mechanical properties, as I mentioned before, with respect to adding the chromium addition to steels. It also, as we've talked with respect to chromium, it gives a greater corrosion at elevated temperatures and a greater oxidation resistance. Now, the oxidation is an issue anytime you're heat treating something, because you're always going to be increasing the temperature of that steel, and as that temperature of the steel increases, it's going to be more subjected to oxidation, which is meaning that the iron is going out and grabbing oxygen from the air, and then coming up with it was an oxidation and iron oxide, which basically from a general standpoint would be something like rust, and so it affects the surface and depletes the surface. We call decarburizing of that surface at elevated temperatures. So by adding some of these alloying elements, that helps to resist some of that oxidation occurrence at those elevated temperatures. So you will always want to, when you're heat treating something, be aware of that and be have some sort of a controlled environment many times in the furnace while these steels are being heated to an austenitizing temperature. All right, the last one here is the formation of what we call hard carbides to provide greater wear resistance. Again, wear resistance, toughness, that kind of goes together, and hardness. And so this wear resistance, specifically with hardness, of course, is extremely important for many, many applications, mechanical applications. And so by adding some of these different alloying elements, it forms these what we call hard carbides, just like cementite is an iron carbide. And cementite, from its properties, are very, very hard and brittle, almost ceramic-like properties. So by adding these, you're going to have a better chance of getting some of these harder carbides formed, which means you have potential for better wear resistance on those steels. Okay, now, before we move on, let me give one little piece of information here with respect to when you designate steels. When you designate steels, you designate them according to AISI or SAE sometimes, American Iron and Steel Institute designations, and usually they come in 4 numbers. And so if we were to give a number, and let's say it was you called out a steel, and for some reason it was a 10, what they call a 1040 ASI steel, AISI steel, a number 1040. What does that mean? Well, we break it up into 4 numbers. We break it into 2 number classifications. The first 2 numbers will always designate the major alloying. The first 2 numbers will designate the major alloying element or groups, alloying element groups or element groups. Okay, that will designate that. Now, and there's specific numbers that go along with that. For instance, anything that's in, you see a 10 or 11 or a 12, that pretty much says it's going to be a plain carbon steel. Where actually carbon is the major alloying element within that steel. Okay, so that's what we call plain carbon steel designations. Anytime you see something again with the first 2 numbers of 10, 11, or 12, those are usually PC or plain carbon steels. All right, and then they have some, for instance, if they're in the teens, like 13 through 15. Manganese is going to be one of the major alloying elements in like a 13 designated, a 15 designation. And then in the 20s, like 23, 25, something like that, then nickel will be the major alloying element. All right, nickel will be the major alloying element. When it gets up into and of course they keep going, 30s, 40s, 50s. Another popular one is a 40. Anywhere 40s, 41s, 46, all the way up to 48s. Those are molybdenum based alloys. When you see the 40s series, and then last but not least, can't leave without talking about chromium. And so chromiums are designated by their 50s. Okay, they're in the 50s. Okay, so I might just put that down here. So chromiums are in the 50s. Manganese is in the teens, the 13s through 15s maybe. Molybdenum, again, is in the 40s. And there goes the timer. Nickel, of course, is going to be in the 20s, we said. And then vanadium, I'm not sure about vanadium. Okay. So those are the major, and that's how the first two numbers are designated. Now the second two numbers are designate the carbon content in hundredths. So it'll be the carbon content in hundredths. So for instance, this 1040 will be a plain carbon steel with, this will have this maybe I wrote off the end of that. This 1040, the 40 is going to designate a 0.4% carbon. Okay, so that's what that 40 means. All right, the last two digits always represent the carbon content in hundredths. Okay, so that pretty much ends that quick discussion on alloying elements and why they're added. And so what we're going to move into now on the next video, which we'll produce as soon as I can get this one uploaded and onto the channel. You might want to check in about an hour or so. The next one, we're going to commence full steam ahead on heat treating and processes, techniques, etc., and then which is going to run into eventually the isothermal transformation or the time temperature transformation diagrams, how we go about getting certain products through these heat treating processes, and then finally all about hardenability. So we'll see you shortly.